Okay, so we're going to be playing around with Desmos a little bit here to now start getting a visual representation of what we've actually been doing algebraically. Like why are we doing it? And honestly, the main reason we do things algebraically is to save ourselves time, because when you graph, it's time consuming, right? So these were the equations we worked with, right? And so what we're going to do now is we're going to go on Desmos and we're gonna put these in, and then we're going to sketch them on here, and then we're going to talk a little bit about them. Okay, so let's get started. So here is the equation right here. It's not showing up because there's this little toggle that's off to the side that's not being recorded right now. And when I toggle it, it's going to show you the equation right here. So I'm going to do that, and then this is the equation. Now you'll notice that this is kind of a funky looking graph here, right? And I'm going to zoom out so you can see something. So hopefully what you see is that this thing has the end behavior, right? So as it goes towards negative infinity, it goes up in the y direction, right? Your output goes up towards positive infinity. Same thing as your input goes towards positive infinity, so does your output. Your output also goes positive infinity. And when you have a polynomial with an even degree number, so 2, 4, 6, 8, God forbid if you have to do something like that, it's always going to have the same end behavior pretty much towards positive and negative infinity for your x, right? And then you'll see here we got some local maxima and minima, right? Because we've got 3 turning points, and the number of turning points is generally speaking going to be 1 less than the degree of the polynomial. So we have a polynomial degree 4 here, right? And the number of turning points we have is 3. Right? And so now what the whole reason we're looking at this, and I'm going to expand this out a little bit and bring this over, right, so we can see it, is we want to look at the zeros. And the zeros are where this thing crosses the x-axis, right? So you're looking at right here, right here, right here, and right here. And so think about what we found, right, when we were doing this algebraically, right? When we solved this, well, this one was x equals 0, this one was x equals -1, this was 3, and this one was 1/2, because remember you add 1 and then divide by 2, right? And so take a look right here. Here's your -1, so that's this one. Here's your 0, so that's your first one that we found. That was our case 1. And then this 1/2 right here, because here's 2, so halfway between 2 is 1, and then halfway is our 1/2 right there, right, is from this, and then this 3, which is way over here, is from there, and then that's so that's kind of how these look. So your solutions, right, that you find are the zeros of this, and they are also where these things cross the x-intercept, right? And that's kind of the connection we want you to make, is it's where this thing crosses the x-axis, right? These are all x-intercepts. So let's take a look at this. All right, so we got our 1, we got that going down almost at 2, not quite, right? And then this comes over here, this goes up. So let's kind of draw this, and when we draw it, we don't have to, it doesn't have to be perfect, right? We're trying to get kind of a close representation of this. So what I'm going to do is I'm going to put my zeros. So I'm going to say, well, I have 1 here, right? And then I have 1 here. We got another one here, and we have another one over about here. All right, so this would be 1, 0, that's 1/2. Obviously, it's not perfectly proportional. And then when we draw this thing, right, it's going to come down, right? It hits this, it curves, goes up, and then it curves again. It comes down, that goes down quite a ways, and then it comes up, and then it kind of goes off into the sunset like that. So this way, right, as x is going to, infinity, our f of x is going to infinity as well. And then here, as x goes to negative infinity, our f of x is going to positive infinity. All right, so you have the same end behavior. All right, so kind of cool, right? And so our x-intercepts that we're going to write down here would be -1, 0, 1/2, and 3, which is also the same as our solutions from when we algebraically graphed this. All right. Okay, so let's try this other one. So we got 2x cubed plus 4x squared minus 16x. Let's see how much of that I can actually remember. I'm going to come over here. So we're going to toggle this off. We're going to go in here, and we're going to call this g of x is equal to 2x cubed. All right, and I'll go plus 4x squared, and then minus 16x. All right, and so look at what we have here. All right, I'm gonna just kind of pan out. So this one is degree 3, right? So in this case, we have the opposite end behavior going on. So as this thing's going towards negative infinity, this thing is also going to negative infinity. And as this side's going to positive infinity for x, your y, or your f of x, is going towards positive infinity. And there are 2 turning points in this one, right? In this case, kind of, really, really far off. So this one's going to be kind of tricky to graph, right? But this one, you've got a local minimum down here. It looks like at about, -10 or so. And then you got a local maximum on this other side, on the negative side of the x, like way up here, like approaching 34, basically, right? So cool stuff, but what we're mainly interested in is these x-intercepts. And so remember, when we solved this, we wound up with 2x times, it was x plus 4 times x minus 2. And we determined that our solutions were 0, right, -4, and +2. And here we go. We've got -4 right here, okay? So that's one solution. Here's my 0, and then here is my +2. So again, we have our solutions are where this thing crosses the x-axis, otherwise known as our x-intercepts. Okay, so we call those the roots, the solutions, the zeros, x-intercepts. They all mean the same thing, right? So now let's go back and let's graph this thing. All right, so when we graph this, right, we're gonna go back to black here, and we're gonna put a point here somewhere around -4. We got one at 0, and we got one at 2, right? And so this one went down, right, and then it went up quite a bit from what I remember. So we're going to change this, right? So I'm going to start up here and then bring it down. So it was going like this, and then it curves, right? And it comes down, it goes through here, goes down not quite as far, and then it curved back up, and then this thing kind of goes like this. All right, it's not supposed to bend like that, but you get the idea, right? So you've got your two extrema, right? And you've got your 3 x-intercepts, right? And so our x-intercepts were -4, 0, and 2. Okay, so it's looking pretty sharp here. That's how this works. And so let's finish this off for our concept development here. All right, so we're gonna go to the next screen. So it says, what do you notice about the zeros of the function compared to the x-intercepts of the function's graph? And hopefully you realize that they are the same. They are the same, okay? And then, what do you notice about the factors of a polynomial function compared to its zeros? Well, when you have like something like x minus 3 is equal to 0, and you solve it, you get x equals 3, right? This is your solution. So your x-intercept, right? X-intercept looks like the opposite, right? It looks like the opposite of the factor, right? So if you've got x minus 3, we've kind of told you to think of this as negative 3. Well, it's kind of the opposite of it. So hopefully when you see something like x plus 7, you realize that the 0 is negative 7 because it's the opposite, right? So this kind of plays into what we did with synthetic division, right? Sort of works along the same lines. And then use what you have learned to find the zeros of this. So we will do this problem in the next slide when I come back, all right? So I hope this has been kind of helpful to you, and we'll see you shortly.